everyone, and welcome. So, today I'm not going to talk to you about how to gain better insight in the insurance industry. Instead, I'm going to talk to you about space. So, let's see. Does anyone here know how we understand space today? Raise your hand if you do. Anyone? Oh, see, a few here. Okay, so today's presentation, I'm going to talk to you about what kind of data sources we have, how we use this data to understand space, and a little bit of why we want to understand space. So to understand what we are doing today, I'm going to have to go back a bit and go into the past. So for thousands of years, we have looked towards the sky on different space phenomena, such as meteor shower, like this image here. And thousands of years ago, we believed that these were omens of either great fortune or horrible disasters. And this was actually recorded down in different media, and this is among the very first data points we have regarding space. But in the 1600s, we got the invention of the telescope, which gave us even more data points. But more importantly, it gave us a refinement in those data points. We had our very first images of space bodies. Take this photo as an example. So this is among the first surviving images of a particular body in space. Can anyone guess what this is an image of? Exactly. This is an image of the sun. And if you couldn't recognize it, it's actually these black dots here that tells you it's the sun. These are called sunspots. And because we now had images of the sun, and we got it for extended period of time, we were able to determine that the sun has an activity cycle that changes every 11 years. And we were also able to determine that this period was closely linked to our activity period on Earth, so the geomagnetic activity. So there's a relationship to what happens at the sun and what happens here at Earth. I will get to this a bit later. Since then, we've had a lot of advancement in technology. Take this image here as an example. So this was taken in 2016 by a satellite. Can anyone guess what this is an image of? Anyone? It's a good guess, but what if I give you this image further away? Can anyone tell what this is? So this is the Comet 67P, where the European Space Agency sent up a satellite and then even landed on the comet. Well, technically it bounced 3 times before it got stuck, but yes, we do have a lander on this comet. Now, images is the main source of information that we have for objects far away in space. Take this remnant from a supernova explosion called the Crab Nebula. So this is a composite image. With that, I mean that this is actually a compilation of different images taken by different instruments in different lights. In scientific speak, it's different wavelength of electromagnetic radiations. So the different colors just means that you have X-ray emission, infrared, radio, etc. Of course, these colors are not actually observed in space. We add them when we are processing the data, so we are able to distinguish what kind of physical sources is behind them. Of course, I don't think anyone is complaining because you get these awesome images. Of course, images is not the only data that we have. We have laboratories around the world that study specific variables, such as magnetic field, in plasma processes. Does anyone here know what plasma is? Raise your hand. Okay, quite a few of you, but not all of you. So here on Earth, liquids, solids, and gas is the 3 matters of states. If you go outside into space, you have the 4th matter of state, which is plasma. So it's a gas that consists of charged particles, such as electrons and different kinds of ions. And the laboratory gives us details about specific variables in specific plasma processes. Then you have computer simulations. Now we have different computer simulation based on how the plasma is treated in theory. So for example, if the plasma is treated as a whole, as a fluid, then it's called MHD simulations. However, if you solve for every wiggle every single charged particle is doing in the plasma, then you have a kinetic simulation. This video here is actually a hybrid simulation, with that the ions are solved for every wiggle, while the electrons is treated as a fluid. Now, just doing simulation won't help you understand space, because you have to verify your simulations, and you have to base them on something to know what's happening in space. So that brings me to the third category, which is satellite data. So we have satellites that are measuring directly in space along their orbit, and they're measuring all kinds of things such as the magnetic field, the electric field, the motions of the charged particles, etc. And we have a lot of satellites. We have several in orbits around Earth. We have satellites at Mars. We have had a satellite around Saturnus and its moons. We have had a satellite at the comet 67P, like I showed you earlier. So we have a lot of data. Now, you might ask yourself, so how does this relate to that image I was showing you further? So the thing is, different regions in space have different properties. They have different magnetic fields, different densities. However, if you look at them in the non-dimensional parameter space, such as this image where you have the y-axis is a ratio between two frequencies, and the x-axis is the ratio between the plasma pressure and the magnetic pressure, you can see that they are grouped very close together. So if we can understand what happens here, closer to Earth, which is way easier for us to send satellites and measure in very good resolution, then we can try to understand what's happening here. Of course, we have to scale it up to match the output that we get from there, but we can still try to reasonably understand it, until at least we can send something there to actually get direct measurements. Now, we don't just study space because we want to understand what's happening at these awesome, strange phenomena. We also study it for our own protection, for our own sake. The sun doesn't just give us sunlight, which we didn't get today, but other days. We also get sometimes massive eruptions from the sun. And sometimes those eruptions head towards Earth, as you can see in this video here. And you can tell that based on these white dots that you can see. This is actually these energetic particles hitting your camera sensor. So this is an eruption that heads towards Earth. And sometimes those eruptions have consequences for us. The most common example used is the Halloween storm that occurred on October 2003. And what happened was that we had massive eruptions for several days that headed towards Earth. And the consequences for that was, among others, we had all flights that were going in polar orbits had to be redirected. Our poles are our weaknesses in the magnetic field. Now, we also had satellites that were permanently damaged. A few of them we managed to send the shut-off command so they could be spared. And some was disrupted, so some instruments stopped working. We had problems with radio communications, and also some transformer burnt out, and we had power outages. So this is just a few things of why we study space. Now, let's get into how we gain insight from this data. So during my PhD, I worked mainly with satellite data, so I'm going to use that as an example. Now, we have lots of data. available because satellite mission usually runs for several years. If you take, for example, this mission here, which is the magnetospheric multiscale mission, it was launched in 2015 by NASA. It has 4 spacecrafts. And if you take all 4 spacecraft and instruments into account, we have right now 96 terabytes of data. Now, to some of you, that might not be a lot of data. However, in space, I'm going to get to why this is a bit tricky later. So the first thing that we do with the data is actually done by the instrument team themselves. They will clean the data and remove obvious instrumental effects, such as shadows and things like that. As a scientist, you also have to do a bit of cleaning on your own, because there are some instrumental effects that will not be apparent, but you have to understand it later through the data. Now, the first thing I always did was that I defined a question. What did I need answer with? Of course, as a PhD student, that's kind of easy, because you already have a picked topic. So in my case, I had electron energization in near-Earth space. So I was looking at how electrons gain energy in different regions in space. So I had a lot of data. I had smaller sets of data because I was looking at different regions. Specifically, I was looking at the magnetosheet, the green region here. I was looking at data here. And when you have a large set of data, you might be tempted to do machine learning. I know, I'm guilty of it. However, space is a bit tricky. So let's do a bit of an example here. Let's imagine that this velocity here, which is, by the way, measured in the magnetosheet here, let's imagine this is a car velocity, which would be an awesome car, by the way, 500 kilometers per second. This increase in velocity here would mean that a person or a computer has accelerated the car. However, in space, it doesn't necessarily mean you have a local acceleration. It can just mean that the spacecraft itself has moved to a different region. So you were standing there and you entered this region here. That's the reason for this increase. It could also mean there's a limitation of the instrument itself, that you're either over or underestimation the calculation of the velocity. So the thing that you have different answer means that training your model, it's very tricky. And you can't really get an accurate result. So what we do in space is that we do a lot of manual, old-school stuff. So how I solved my problems was that I actually did search algorithm. I have parameters that I know will be changing physically based on energization of electrons. So I sorted through all the data available with those parameters, and I did plots like this. And then I had to manually go through those plots to determine, first of all, did the search algorithm work? Second of all, is there something interesting happening here, like acceleration, or is this just that I'm moving to a different region or something like that? Now, I'm not going to go into this panel in detail. I just wanted to show you as an example. The different colored lines here just gives you the measurements of the different spacecrafts. Now, this image here is actually from one of the events I found, the first one in my search algorithm, and it actually became a published paper, and I was able to find which kind of acceleration mechanism was responsible for the energization of the electrons. So this is a bit of a shameless plug here. But that's how we understand space. We pose a question that we want to find the answer to. We use different kind of data sources. And usually we have to combine different kinds of sources. So a lot of the time you will look through the satellite data, but that's just along the satellite's own path. To truly understand what's happening, you need, for example, a computer simulation that you can try to understand how the whole region is changing, what kind of complex changes is happening. You will look through the data, visualize it. There's a lot of plots and a lot of manually going through those plots. And then you just do comparison with theory when you try to figure out what's actually happening physically. And sometimes you figure out that maybe the question I posed wasn't that good. I have to refine it and go again. And maybe some of you here are data scientists or know how data scientist works, and you might recognize a lot of these steps. And that's because understanding space is data science. That's exactly what we are doing. Thank you.